Steinhauer here. Welcome back. We'll start today's video with a review question covering material from the last class. And today's question is, what happens when an electron in an atom drops to a lower energy level, as seen in this diagram? Here we have a model of the atom. We've got the nucleus in the center. We've got a couple of electron orbitals here. What happens when an electron jumps from a higher energy to a lower energy? Is a photon absorbed? Is a photon emitted? Does a photon move to a higher energy level, or does nothing at all happen involving photons? Okay, make your guess. Okay, to understand what happens here, when you think back to last time and remember conservation of energy, right? The higher you go in energy, or the further away from the atom, from the nucleus you get, the electron gets, the higher the energy it has. And energy can neither be created nor destroyed. So if an energy is going to jump up to a higher energy level, that atom will have a higher energy, and that energy has to come from something. If an electron absorbs an energy, it absorbs something, it has to move to a higher energy level. That energy has to come from somewhere. Typically, it's a photon. So if a photon comes along and an electron's in a low energy state, and that photon has exactly the right amount of energy to jump that electron up to a higher energy level, that atom can absorb that photon and the electron can jump up. Conversely, what this question is asking, when an electron jumps from a high to a low energy state, that electron loses energy. That energy has to go somewhere. And the place where that energy goes is typically into a photon. What will the wavelength of that photon be? It will be a photon whose wavelength corresponds to an energy, which is exactly the amount of energy that the atom has lost by having that electron drop from the higher to the lower energy level. So all of this stuff just has to conserve energy. And so and this question asks, what happens when an electron jumps from a higher to a lower? That is a loss of energy. That energy has to go somewhere. And so the atom must emit a photon. And the answer would be B here. Okay. That leads us directly into the thing that is the next topic in this class, which is what are the three basic types of spectra? But first, before we really talk about what the types of spectra are, we need to think about what a spectrum is. And so here we have an example of a spectrum. This is a cartoon version of a spectrum, but it is a cartoon version of a real spectrum, specifically of the planet Mars. And you can see some interesting features here. But let's talk first about what a spectrum is in general. A spectrum is a representation of how much light we are getting from an object as a function of wavelength or as a function of frequency. So it's often plotted as intensity on the y-axis, and intensity is just how much light we're getting, how much energy, how many photons per second, what is the brightness of this object. And on the y-axis, on the x-axis, we have wavelength, right? In this case, we are spanning the visible part of the spectrum. Here's blue, green, and red. In fact, only this part from here to here is in the visible part of the spectrum. This is in the infrared, and this down here is in the ultraviolet. But you can see no object has exactly the same amount of light coming from all different wavelengths. There is some distribution, and that distribution is called a spectrum. And you can see we have three different kinds of spectra. By the way, the plural of spectrum is spectra, which is why I've written that here, and I'll be saying it a lot. Anyway, you see three different kinds of spectra here. One is, and I'll highlight these. I'll highlight them blue. How about that? One is a continuous spectrum. So I'm going to highlight the two continuous spectra we see here. Here is one of them, and here is the other one. Continuous spectra are characterized by roughly smooth distributions over large wavelength ranges, right? So it's not that Mars has exactly the same brightness in blue, green, and red, but it's not varying up and down drastically. It's varying smoothly across a very large range of wavelengths here. And we call that a continuous spectrum. And you see another one over here. We'll talk about why Mars has two of them and why you get these peaks happening in different places later on. That's important. A second type of spectrum is this type of spectrum here. These are called emission lines, where you see almost no underlying flux, or maybe you have a continuous flux underneath it, but on top of that, you have some very specific wavelengths at which you're getting a lot more light. That's interesting. So this is an emission line spectrum, and conversely, you can have absorption line spectra where, again, superimposed on top of a continuous spectrum, you have some colors, some wavelengths, where you are missing the light that you would expect to be there. Somehow it has been absorbed and taken out of, you have this underlying continuous spectrum, but at certain colors and certain wavelengths, you can see the dark lines here, there have been photons that have been removed from the spectrum. So let's try to understand, in the context of atoms, how these spectra are made. And we'll start with continuous spectra. And continuous spectra are really important, and we're going to spend the entire next video talking, maybe a subsequent video talking about continuous spectra. But here's what you need to know. Continuous spectra are made by hot, dense sources. For instance, an incandescent light bulb. An incandescent light bulb works by running electricity through usually a tungsten filament, and that tungsten filament represents the hot, dense object at the center of your light bulb. And if you run enough electricity through that tungsten filament, it will get quite hot. And when it gets quite hot, it will glow. And it will glow with a continuous spectrum, right? It will be roughly even distributions over a large range of wavelengths. So things like tungsten filaments, things like rocks, things like planets, things that you can't see through, emit at all wavelengths. And the reason for this is because these photons are emitted by the random motions of charged particles in the object itself. And since molecules, since atoms in these objects are vibrating at lots of different rates, they're giving off energy at lots of different frequencies. And that corresponds to lots of different wavelengths. And you get this nice broad distribution. Now, what color this is and where it peaks is highly dependent on the temperature, but we'll come back to that later. For now, all we need to know is that hot, dense objects viewed directly give you a continuous spectrum. Okay, let's think about absorption spectra now. What if you take that hot, dense object and you place in front of it a thin, transparent cloud of gas? What's going to happen? Well, again, this object, the hot, dense light source, is producing wavelengths, photons of all different wavelengths, right? All the way across the visible and into the infrared and into the ultraviolet spectrum. Those photons will pass through this cloud of gas. This cloud of gas is made up of atoms. Those atoms, let's say it's a hydrogen gas. Let's say all of the atoms in this cloud of gas are hydrogen, right? We know hydrogen has specific energy levels of its electrons. So if there happens to be a hydrogen atom sitting there, let's say in the n=2 energy level, we know that there's a red photon that is the energy equivalent of the gap between the n=2 and the n=3 energy levels in hydrogen. That is the H alpha line. So if there's a atom in this cloud of gas sitting at the n=2 level and a red photon of exactly the right wavelength comes by, that photon will be absorbed by that atom. And that atom will have its electron jump from the n=2 to the n=3 level. And that photon will be removed from the stream that's coming through this particular region. And so when you look at this spectrum of the hot incandescent bulb passing through this cloud of gas, you'll still see the hot incandescent bulb and spectrum underneath, but you will have some things removed from it. Specifically, you'll have holes in the spectrum where atoms in this cloud of gas have removed specific photons with specific energies corresponding to the pattern of energy levels in its atom. If you had a cloud of helium gas, you would have a different set of energy levels, which have a different pattern, and you would get a different set of lines over here. In fact, we can use this to figure out what gases are made of. Anyway, I'm getting ahead of myself. Let's think about an emission line spectrum, because it's a very similar arrangement to get an emission line spectrum. To get an emission line spectrum, well, what happens? Let's go back to our absorption line spectrum. We've got this hot light source. It's heating up our atoms in our gas by making their electrons jump up to higher energy levels. Well, we know that electrons like to be at the ground state. In fact, they will jump back down to the ground state automatically if they're left alone for too long. And so you might think that those would be represented in the spectrum, and they are. If this cloud of gas weren't re-releasing those photons in a different direction, this might go down to 0 in some cases. But when a photon gets absorbed by this particular cloud, it gets re-emitted in a random direction. So that photon that gets absorbed by an atom in here will get emitted in any direction, in a random direction. Some of them might go that way. Some of them might go that way. Some of them might go that way. There'll be a perfectly spherical distribution of where these photons actually go. And so if you're looking at this cloud of gas without this hot light source directly behind it, instead of seeing a continuous spectrum with an absorption line at that particular wavelength, you see no background, and instead see this cloud of gas glowing at exactly the same wavelengths that were removed from the gas on the way through. So the same cloud of gas can produce either an absorption spectrum or an emission spectrum, depending on how you're looking at it. If you're looking at it with the hot light source behind, you see this absorption spectrum. If you're looking at it without the hot light source directly behind it, then you get an emission line spectrum. And you're only seeing this cloud of gas de-excite and those photoelectrons being generated. So any thin, low density cloud of gas that has been heated up by some source, like a light bulb, will produce an emission line spectrum. So as I mentioned before, whether you're seeing this cloud of gas absorb photons or emit photons will depend on whether you're seeing it with a hot object behind it or not. A gas of hydrogen atoms can produce either an absorption spectrum or an emission spectrum, and it will happen, those lines, whether they're in absorption or emission, will happen at exactly the same energy levels. And so they'll happen at the very same wavelengths. For instance, this H alpha line, as we mentioned before, from n equals 3 to n equals 2, will produce a 656.3 nanometer line in absorption or emission, whether you're seeing, depending on how you're seeing this actually play out, whether you're seeing it bumped up or whether you're seeing it more bumped down. And as I mentioned before, every atom has a unique set of electric and electron energy levels. And so each atom has its own unique fingerprint of which sets of lines are from that element. So for instance, here's a continuous spectrum. Here is the lines of sodium. Here are the lines of hydrogen, right? We already talked about hydrogen. Here's H alpha, that red line. Here's H beta, that teal line, and H gamma and H delta, the blue and indigo lines. But look at calcium, has so many lines. Mercury has so many lines. In fact, many street lamps for a long time were mercury lamps. And mercury lamps do not have continuous spectrum. They are fluorescent lamps, and they fluoresce at particular wavelengths corresponding to these lines. If you were to take a spectrum of a mercury lamp, you would actually see not this, but this down here. So that's fun. In fact, here's a question for you. This is, in fact, an image of the solar spectrum. It's very high resolution spectrum, meaning we're getting very fine detail on lots of features in the spectrum. And in fact, it's so long that we wouldn't be able to put it on one slide. So they've cut it up and pasted it into a ribbon. But at the top, you've got the reddest wavelengths down all the way. The spectrum is going in this direction, and then it continues on the next line, and the next line, and the next line, with the blue on the bottom and the red on the top. So the question is, what kind of spectrum is this? Is this a continuous spectrum, an absorption spectrum, or an emission spectrum? What do you think? Okay. Again, this is kind of confusing, and maybe this is, so let's talk about this. We're seeing one representation of a spectrum, and that is how bright it looks to us, right? And so we see the brighter it looks, the more light is coming from that particular place. And these dark lines, of course, are emission lines. This is one way to look at a spectrum. Another way is to plot intensity versus a function of wavelength. And then the height, the y-axis, tells you how bright it is. And you can see the absorption lines there. But this is definitely an absorption spectrum. You see the rainbow continuous behind it, right? Red and yellow and green and blue, all wavelengths represented, but there are holes in it. There are lots of holes in it. Here's a big hole, here's a big hole, here's a big hole, here's a big hole. Those are very strong absorption lines in the solar spectrum. In fact, this is at 656.3 nanometers. This is the H alpha line. These two are from sodium, right? We know, in fact, this is how we know what the sun is made of. We see fingerprints of all of the elements pretty much represented in the solar spectrum. We can even measure how much iron is in the sun. We can measure how much calcium is in the sun. We can measure how much oxygen is in the sun based on how strong these lines are. The more of that element that is there, the more absorption we should see from that element, the deeper and the stronger these lines should be. So that's fun. But the question is, why is this a solar spectrum? I told you that why is this an absorption spectrum? I told you that an absorption spectrum was a hot, dense object with a thin gas cloud on top of it. What is the hot, dense object, and what is the thin gas cloud associated with the solar spectrum? What do you think? Well, you can't answer me, but I can tell you. The hot, dense object is the interior of the sun. It is the sun's photosphere, or layers just below the sun's photosphere. If you go deep enough, the sun does become a hot, dense object, no doubt. You cannot see through it. It is opaque. But the sun, as we'll learn later on when we talk about the sun, has an atmosphere. It doesn't just have a solid surface like the Earth does. In fact, the sun just gets less and less dense as you go out, but eventually you are so dense that you're no longer opaque. You're now transparent to light. And so there are still lots of atoms out there. And so the sun's atmosphere, the chromosphere, if you like, is the region through which these photons are traveling to be absorbed by hydrogen atoms and carbon atoms and iron atoms and oxygen atoms and everything else. So that's the solar spectrum. All right, I will stop there. We'll come back in the next video and talk about how light can tell us about motions of things in the universe. Thanks.